and some formal definitions also, and then I think more questions can come out, right? Right. So of course, I will assume that you know what are groups and some examples and so on. So group actions, right? So let me just give a definition first, okay? The formal definition would be, you already know, but I'll just define it. So we are given a group and we are given a set. Okay. And this is a group and then set. Okay. And then we say that a group acts on a set X. This is, you can use any definition you want. This is one definition, that this thing, this is a notation. This is a notation for this function. There is a function like this from G cross X. So G cross X is just the Cartesian product, which means you take an element of the group and you take an element of the set on which it is acting. Okay. And you return an element of the set. That's the action. It pushes that object to some other object potentially. It might fix it also, but right. And obviously, this should satisfy some rules, right? Yeah. And uh, yeah, just a minute. And I can say it like that, but I want to say it. G cross X to X considered three things. And yeah, all this can be said better if you have a, say it's a homomorphism, but without that language, it's, yeah. So without that language, I will just say it like this, okay? That this is just denoted by this dot, okay? And maybe not by dot, we'll just not write anything. We'll just say this goes to this, okay? And then basically the property that should be satisfied, so that I should write it such that, because that is what is in the definition that should be satisfied for you to call it a group action. Otherwise, it will not be a group action. It may look like an action, but it will not be. So there are the obvious things that you, this will make sense, right? Because G1 G2 dot X will make sense. This is the image of G1 G2, okay? And if you want to call this phi, this is same as image of, yeah, this. So this is demanded because this is not obviously same, okay? It is not like, will not be same a priori, because this is a different element acting on X, and this is G2 acting on X, and then the result may again G1 is acting. So it's could be different, but it is should not be, and it is not different. The definition demands that it is the same. And then there is another property which is probably redundant, but is still stated. Okay, that's it. So this is the definition, and equivalent definitions can be given, but is the definition. Now the question is, why are we considering group actions? So the definition, why group actions? So for that, you should first understand that groups arise out of symmetries of objects, right? You take some object and then you study its symmetries, and that way you get a set with an operation, right? So basically, it's like you start with a set, right? And this set could be, for example, you could keep in mind like a pentagon, a regular pentagon. Okay? And maybe it is, well, it does not matter, but maybe we will think of it as pentagon in R2. Let's just think of it like that, a regular pentagon in R2. So we start with the set. And then second step is to understand the symmetries of that set. Right? Symmetries of the set. Right? So what is symmetries? What is the definition of symmetry? Well, you can take it as all the functions from R2 to R2 which fix the vertices of the pentagon. Fix meaning that which fix the set, 5-point set, meaning that they could permute, but the set on its overall it's fixed. Okay, so a point will in that 5 set should in that 5 element set should again go to a point in that 5 elements. Okay, that is what a symmetry is. A symmetry is a function which fixes the object on the whole, but not pointwise. Okay. Obviously, you have a feeling of symmetry, everybody has, but it's just a definition which you maybe also know. Symmetries of the set. And then you figure out that, then you see that the symmetries form a group. Any of the symmetries can be composed, means the collection of functions you get in the process can be composed, right? Inverse of such a function is also such a function. And so that forms what is called a group, right? So the set of symmetries, set of B under composition forms a group, right? So this is how groups come, okay? But the problem with groups is that a group, as the mathematical definition is a very abstract object, right? It's just a set with an operation, okay? So sometimes when you have the abstract group, you do not know where it comes from, right? You may not know which object, right? And which object did you consider, or I should just say that this G the symmetries of some object, right? If you start with an abstract group, you start with this G is just an abstract G, right?
Yes.
Abstract. So then the question, so this is A to C is you understand. From a set you get a group. But then if you start with a group, how do you come up with a set? That is the question. If you start with a group, then is there a set, right, such that the symmetries of the set is equal to this group? Means set is S, right? We want to find that set S. You could, in some sense, right? That is means one of the things, right? Why? Because that could help us to understand the group better. Okay, because if a group is given, some multiplication rule is given, how do you know what the group is, right? Meaning that is this group made out of some simpler groups by some product operation or some direct sum operation? That's same, but yeah, other operations. So basically, to understand the structure of the group, okay, does it have an element of order 10? Right? How do you know? If you know that this group was acting on an object, sort of a rotation on some object with 10 vertices, then you would know, yeah, if it is rotating, then there is a rotation of the smallest kind, then you know that there will be an element of order 10, right? So just a small example. So, I mean, not even example, I'm just saying in words, right? So you could understand the group if you knew that there was an object whose symmetries this group is, okay? And now group actions enter the picture. if you again go back to this first point, yeah, then this object and the symmetries. Now, if you take this G, right, and then you take some G in this G, right, then you can make this G act on the set S. No, because this G is actually a function from S to S, right? Because that is what it was defined as. It was a function of R2 which fixes that set, which means that it's a function from the set to the set. Correct? So when you start with a set, you take its symmetries, it forms a group. But this group that you get obviously acts on that set. What does it mean? It just means that the elements of the group are by definition functions on the set, right? Which means that for every element of the group and every this thing, you can just define this. Well, this is just f of, where it's just the function G acting on the element S of the set S, right? Sorry, this is bad note, right? For example, if you look at this and you see that rotation by whatever 360 by 5 is 72, right? Rotation by 72, R72, this is an element in this group, but this also acts on this set now, right? So every element of the group acts on this set, correct? And so in that way, you get a group action. Correct? I mean, this is a group action is given to you. This is the perfect group action. Right?
So if G is the function from S to S, we are writing that as a Cartesian product, G cross X going to S.
Yes, every element of G is a function from X to X. Every element of G.
Oh.
Right, correct, no? Every element of G is a function. For a different G, you will get a different function, right?
Yes.
Yeah. I mean, we are collecting all those functions and calling it phi, but that phi is a different sense. But for every fixed G, you get a different function, right? Just like for every small G, you get a different symmetry of the object X. Okay.
Yes.
Right, and obviously that symmetry which you get is obviously a symmetry because it's an invertible function, because G inverse is there, because it has an inverse function which is G inverse. G inverse will actually act like the inverse function, the inverse of the bijection from X to X given by, right? So this G gives a map from X to X, but the G inverse also gives a map from X to X, right? And they are inverses of each other by all these rules which are given. So these are the kind of things, okay? But then why is it interesting to find group actions for abstract groups? Because this was basically coming from this group was coming from the symmetries. But even when you're given an abstract group, you would like to think of an object such that this is the symmetries of that object. And how you get a chance of getting this if you can think of some set such that the group acts on the set. Then you can give yourself a chance, right? Then you will basically, S will be like the object on which whose symmetries G is. Yeah. I mean, there are some problems, but okay, let me say this a little more carefully. This set, you want this, right? Now, suppose you get G acting on S, right? Then what happens? Then basically, as you said, right, every element of G makes a function from S to S. Every element of G gives a symmetry from S to S, right? So you are somewhat getting that every element of G is a symmetry of this, of some set. But there are some problems, which I will not say right now. Okay, yeah, then some quotient group and so on. But, okay, a very easy, rather intermediate type example of that is basically the isometries of the plane, right? So you basically, what happens in that, and the isometries of the plane story start with R2, which is the plane, and then you look at the isometries. So basically, you look at isometries You start with the plane and you look at isometries of the plane. So what is this? Just isometries. This is just functions from R2 to R2, which are isometrics, meaning that d of x comma y is equal to d of isometric. So isometric, so that doesn't disturb the metric. Okay? Application of f doesn't disturb the metric. Before and after it is. So see distance preserving functions. So if you collect this set is a group. Right? This set is a group. Obviously, because you can see this condition ensures that it is bijective and so on. Though you have to prove those things, it's not completely trivial that this implies bijective. But if you believe it, then it is a group. But then, I mean, what do you know about this? That's the problem. Like this, it looks like a complicated group. Okay, but you can prove that this group is made out of two slightly simpler groups. Okay? And there are two things I've said. One thing is simpler group. For this, you need to know group theory. Why is one group simpler than the other, and what is made out of? What does this mean, right? This would be, how do you make a bigger number from a smaller number? Do you add? Do you multiply? Do you do some other exponential or something? Yeah. Here it's there, but what are the simpler groups that we first say? The first simpler group is the orthogonal group. What happened? This is just R2, so this is O. Orthogonal group, you know, right? This matrix theory, A times A transpose equal to identity. Those kind of groups. Basically, this will just be basically cos theta, sin theta, cos theta, sin theta minus sin theta, just the rotations. Just rotations. So it is made out of this thing, which you can just think of 2 by 2 matrices and simple 2 by 2 matrices, which are that kind of matrices. That's just that, okay? And made out of is slightly complicated, semi-direct product. Okay. And when you say, yeah, so semi-direct product of this with something. And that something is actually also very simple. It is just the reals under addition. This other group. Okay. Now, this group is basically also just simplest group, right? The reals under addition. Simplest group. And this group is also quite simple. And this operation is there, which is slightly there, but okay. I mean, for this, I have to tell you what is what, but right. So let me tell you, you know, in a slightly simpler way, how can you believe this, and how group actions can come into the picture to understand to prove such a thing. Okay.
And the name of that operation?
Yeah, this name of this operation is semi-direct product, right? This you should study. If you have studied group theory, then this you should have covered. If you have not covered, then you should read it. Semi-direct product. Yeah, not the simplest operation, but it is there. Natural operation. And this. So this basically says that there are rotations, and this basically says that there are translations. And this says that everything can be made out of rotations and translations. Okay. But how do group actions help us? Let us think. So maybe it can be something like you make this. Say, I don't completely remember this. I don't remember, but let's see if I can build it. So if you look at isometries of R2 and you act there, obviously you acted on R2. Okay? And then you look at, so have you studied stabilizer of an element?
Yes, stabilizer of an element.
Stabilizer of an element under a group action. So given an element X, right, we have something called stab X, stabilizer. So G is acting
Yeah,
on
that
X.
is
Just
G
stabilize
belongs to G.
it. Right.
That
Correct.
gives GS equal to X.
Exactly. Stabilize it. Perfect. So in this case, obviously, this is our group and this is our set. So G is acting on X and this is stabilized. So you look at this action, and this action is obviously a transitive action, which means you can go from any point to any point, given any X and Y. There is a G which will take G of X to Y. That is quite obvious. I don't need to tell you. Transitive action. But now you should look at the stabilizer of 0. Stabilizer will always be for some point in the set, correct? You agree? So stabilizer of 0. Okay. So what will be the stabilizer of 0? What are all the isometries which fix the origin? That is the question, right? And that is, I don't think it's a trivial statement. Again, I can go into that, will become a different thing. I will not go into it. And that is actually O2. Yes. Okay. This you will see, because if it fixes the origin, you have to prove this. I mean, it's not. It's first to show these are affine transformations. Then you have to show. But you can sort of believe, because O2 certainly fixes the origin, because O2 is linear transformation. So O2 fixes the origin. So this is O2. And
But we are not getting the O2 directly. We will get some elements of O2, right? O2 is the whole group.
you will get all of O2. Yeah, meaning that
Yeah.
if you take all the isometries which fix 0, 0, you will certainly get everything in O2. That is clear. But you will not get anything more than O2. That is not clear.
Oh.
Right. O2 you will certainly get. O2 is just a rotation. So rotations are certainly rotations are isometries and they fix the origin. That is fine. So O2 is there, but nothing more is there that you have to, that is probably you don't know. So that has to be shown. Yeah, actually, yeah, maybe group actions are not very useful, not totally useful for this particular thing. Maybe, yeah, but we can prove this in a different way, but group actions are not, yeah, maybe, yeah. So I told you the intuition for this. I can prove this, but you don't quite need group actions the way I am doing. There's something in this which needs the group actions. So let's try it. So if I consider the stabilizer of a point, then
Okay, here isometry of R square is acting on R square. So
Ah.
what's the action here?
I've told you, no? It's the functions. So what will be the action? Functions. So yeah, so what is the action? Maybe it's just the language. So you take something from isometry, take G, take a point in R2, X. What is the action? Just the function corresponding to G. G is a function, right?
Oh.
Right? Maybe I just write F. Why write G? Take an element F from here, right? And take an element X from here. And the action is just like, what else can it be? Nothing else. It's just only one choice. Okay. So that is there. Here, yeah. So in this particular thing, that I can show, but that's not going to help you in this. That's not going to be helpful in this. this. So if you take isom R2, so I wrote something wrong, and that is why I'm struggling. Yeah, it is R2 under addition, right? It should be R2 under addition. Because I mean, I'm referring to translations. So translations should be R2. Translations of R2 are just R2. Right? I mean, because every translation is given by an element in R2, right? So taking the plane, so tell me some translation, translate by 1, 2, and so on and so on. And that's also a group. So this is basically the group of translations under addition. So it's not R, it's R2. Sorry. Okay.
Translation means?
Translations means translations, right? Translations means this. Translations means you take R2. So I'm giving you a particular translation. So let's say you're translating by 1, 1. So this will be a function from R2 to R2, right? Which will take x, y to just translate it. Just see the geometrical picture. Translation.
Okay.
Yeah. So that's what, and those are obviously isometries, right? Those are the easiest isometries. And the other ones are these. And everything can be made out of this. So now let us just contemplate. So we have G and we have this tab of the origin. Okay. And do you know the orbit stabilizer formula in group actions? So
that is orbit of S. Yes.
Yeah, something like this, right?
Yeah.
I mean, there are some conditions, but something like this, right?
Actually, this X will be orbit of.
Correct. Yeah, you're right. You're right. You're right. But in this case, since it's a transitive action, so the orbit is all of the set. But you're absolutely correct. This is the formula, right? And this is like size, right? Yeah. So in our case, will become isom of R2.
But I don't know how that formula came out.
That is right. I understand. But you can believe the formula, right? And you can feel it also if you think. But anyways, since I'm just giving you an overview, and if you look at this isom of R2, and as this is a G, and stab of X is O2, which is the orthogonal group, right? Then the quotient is the set. What is the set? The set is R2. You see, this is quite related with this.
Yes.
And how did we get this? By all the formulas of group actions. Obviously, we have not proved a lot of things, but still, you can see that you have to just somehow develop some mathematics to send this O2 here. Okay, that is the thing. Okay, but obviously, I might be saying, I'm not saying too many things wrong, but I'm certainly not proving anything. Okay, means you have to prove that, because here this was size ka quotient of numbers. Suddenly here I've done quotient of numbers. You have to question that, right? Sorry, quotient of groups. So this has to be a normal subgroup, which you can prove. And then this quotient is equal to R2. And this and this are quite believable, quite related. But for that, you need some more mathematics. But you see, this is the beauty of group action, that they can at least tell you that, look, this is the relation. That you take all the isometries, and if you kill the ones which are fixed in the origin, then all you are left with the translations. And with group actions, it becomes easy to see, right? It's like you begin with your intuition that people found that isometries of R2 में ज़्यादा कुछ नहीं मिलेगा. You will only get rotations, and that is like ancient knowledge, right? Rotations and reflections and so on. Because everything can be gotten by rotations and translations and reflections. I'm sorry, rotations, reflections, and reflections are different. Rotations, reflections, and this is like ancient knowledge, right? नहीं मिलेगा, but what does it mean? Means what does it mean that from here you can build everything? How do you make a precise mathematical? So group actions do some part of the work, right? Okay, and little bit more by some semi-direct product and group decompositions and so on, their work can be completed. Okay, and this. But read this. Group actions is well written in Artin's book, Artin's chapter on symmetries. That's because that's a common reference. Because once you learn to read an author, then you can understand what they are trying to say more easily. Because how they put their commas and what they mean by the long dash. It's all about reading that. If you can read that carefully, then you can read everything, right? That's the thing, right? Yeah. So this is group actions are very, 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 very useful. Okay? And this was sort of the first part of that course on groups and geometry. Obviously, I don't remember or recall all, but I would love to discuss all that. But yeah, first you do the basics, and I suppose we cannot discuss other things right now. Yeah. All right. So I
Okay,
will.
can we do class on Thursday?
No. Thursday I cannot do because actually I have someone else has had asked me, so I'm to do some problem solving session with them. Otherwise, I would have done. Yeah. Okay. I can
So
do on
before Sunday, anytime.
and actually Sunday I may not be able to do actually. This Sunday I'm not sure. Okay.
Oh, okay.
So that is why we can do on Friday. Is Friday okay?
Friday morning?
Morning, what time?
Friday is Moharram or something, I guess. So college maybe not.
Yeah,
will
don't
be
go to
closed.
college. Just tell them it's tomorrow. Yeah.
I have attendance compulsory. Like I can't miss college.
Oh, okay, right. So what time morning, if you can do?
Morning, anytime I can do, but I'm not still
Confirmed.
like
Okay. Then you can
properly don't know
yeah,
that.
then you will confirm me. And if morning doesn't work, then evening also works. Okay. Yeah. Evening means at 8:30. Friday evenings also work. Okay. And yeah. And Sunday I may not be able to do. Okay. Sunday I have a tournament at play.
Tournament of what?
I play table tennis, right? So in a Bengal, but this one is not a Bengal. There's also a Bengal tournament on in SAI Sports Academy of India, but I'm not playing that one. I'm playing a league tournament. This is in Bhawanipur Bayam Sangha. You may know, it's a table tennis club. So there is it's a tournament. Let's see how it goes. Yeah.
Have you ever like played TT in school or college level or something?